Welcome, everybody, to this week's session of our CTE Momentum series, your Place in Space Challenge. If you have any questions, please put it into the chat, and we are going to be opening up in a short while for questions. This workshop is going to be shorter than last week's. Last week was really intensive. It was fantastic with our subject matter expert. Today's session, I'm actually a resident expert. So, the thing is that in researching everything, I actually realized that these topics are firmly within my skill set as a chemical engineer who practiced for way too many years for me to mention, because then all the students who are in the room are going to be thinking, oh my heavens, she is so old. So let's get to it. What I'd like you to do is, as I mentioned, please post your questions in the chat during the main presentation, and let's have a look at our agenda for today. First of all, we're going to go through an introduction to the CTE challenge and the role that MaxIQ Space is playing. We have got background to the topic with some examples, and then we'll have a very open discussion. Let's have a look at perhaps the proposals that you're working on at the moment. Let's actually maybe have a little bit of a Q&A around that, and also questions for the challenge team. I can see that Rebecca has joined us. So Rebecca, I know this is like, I'm really throwing this Hail Mary at you, but I was wondering if you wanted to just give everybody a little bit of background around the challenge this year.
Sure. Thanks, Judy. So a little bit of background. This challenge is the first in a series of annual challenges held by the U.S. Department of Education. That series is called CTE Momentum. CTE Momentum intends to increase access to career and technical education and prepare students for rewarding careers. And the Your Place in Space Challenge is the first one. And the aim of the Your Place in Space Challenge, what we're asking students to do in their classrooms is to submit designs for a product or service that will contribute to space missions and exploration. And we hope that in doing so, students will be inspired to envision and pursue the careers that they can have in the space industry, really understanding the diverse group of professionals that contribute to a robust space industry and also contribute to our lives here on Earth. So that's the vision for the challenge. There's a ton of information on the challenge website, as I'm sure Judy has shared, and I know that this recording will be published there afterwards as
well. Great. Rebecca, thank you so very much. And so let us go back to our slides. And the role of MaxIQ Space, what we have done is, as a group, MaxIQ Space is made up of a bunch of engineers who really want to engage youngsters so that they can have the most fantastic careers in this rapidly growing space industry and participate as the Artemis generation and the Mars generation. So what we've done is, in terms of the CTE challenge, we have offered up to do mentorship. We also have some kits that we're going to be handing out to some of the finalists and the winners of the challenge. So without further ado, let's have a look at our two examples. So the first example we're going to look at is water recycling on the International Space Station. So fresh water can be supplied to the space station, and sometimes it is. Unfortunately, it's really expensive to get it there, and from a fuel perspective and also a volume perspective. So the International Space Station relies very heavily on advanced water recycling systems that purify wastewater, including sweat and urine, into clean water for drinking and other uses. So what we have here is a prime example of a closed loop system that minimizes waste and ensures sustainability. So from an engineering perspective, closed loop systems have been in operation actually ever since the beginning of the Industrial Revolution, to quite a large extent. Even when we had steam engines, a lot of that steam, once it had gone through the turbine, was recondensed and then refed into the boilers, because there was just limited resources of how much water there was available to run factories, etc. So this concept of a closed loop system goes back all the way to the beginning of the Industrial Revolution. So we can see here in the blue lines basically represent the cycle of the water, and then these pale gray lines represent the basically the gas or the air, the different gases or the air recycling. So the thing is, what we can see here is that the water is also used in terms of the process of cleaning the air, scrubbing out carbon dioxide. Carbon dioxide is highly soluble in water. So the thing is that it's very easy to actually strip the carbon dioxide by using water. Also, the thing is that what happens is that we've got this Sabatier system, which is really some cells here where we're using reverse osmosis and actually removing a lot of the methane, which is generated probably by the toilet, if you don't mind me saying so. And also the thing is that what often we can do is we can actually strip out the hydrogen, which then actually is also used in this process, almost like from a fuel cell perspective. So this is a closed loop system in terms of all of the gases, the air inside the space station, as well as the water recovery system. So on the International Space Station, we need to use technologies like distillation and reverse osmosis. And the reason for that is because we can't rely on gravity. When the space station is in orbit, it is in a microgravity scenario, environment. In fact, it's, let's say, 2, 3, or 4 micro Gs of gravity is being experienced. So to a lot of people, that is essentially weightless. So the thing is, what we would do on planet Earth is that we would have a filter system where we would maybe have cloth filters that we ran the water through, maybe a very fine mesh or otherwise a sand filter. And we would be relying on gravity for that water to then flow through or sink through those different filter media. So the thing is that what we can't do that on the International Space Station. So we have to rely on other forces to assist us. And so distillation that's the process where we are evaporating something and then we're condensing it again. So what we would do is we would have a look at evaporating, let's say, the water, the dirty water. And then what we would do is when we condense the water out, it would actually be pure water. I think as a number of you know, you can buy distilled water, which is almost pure, almost 100% pure. It may have some small traces of other elements in it, but so the thing is that distillation is used very well when we're looking at liquids, because we can change the phase between gas and distill it then again as a liquid. And then we also use reverse osmosis. And osmosis, what we have is we will have a membrane and there's a high concentration either in gas or liquid of a particular, let's say, metal or a contaminant on one side of that membrane. And then by applying pressure or vacuum on the other side, we are able to actually purify that, so that we make sure that the contaminant stays on one side of the membrane, and then that can be sorted out and that can be removed on its own. So reverse osmosis is really absolutely fantastic. Osmosis is a very natural process. When we refer to reverse osmosis, that is when we actually are applying either vacuum or pressure to the system to get it to actually behave in the opposite way of how it would naturally behave. So we're putting some work in, so that what we're doing is that we're able to reverse that process. The second example we're looking at is the MaxIQ experiment. So the MaxIQ experiment flew with the Mars Perseverance rover. So in 2022, the when the Perseverance rover began its mission to Mars, and on Mars, it carried a MaxIQ experiment, and that is an acronym for the Mars Oxygen In Situ Resource Utilization Experiment, which converts the abundant carbon dioxide in the Martian atmosphere into oxygen. So this is a crucial step in preparing for human missions to Mars, where resupplying from Earth would be extremely challenging and, of course, very expensive. It would take a very long time as well. The trip to Mars is months, if not years. So if we're running out of oxygen, we're not going to be able to wait for a resupply. And one can only really apply this when one has an abundant situation of carbon dioxide. So, for example, the MaxIQ experiment wouldn't work on the International Space Station because the amount of carbon dioxide in that atmosphere at any one time is going to be way too low to actually be able to then extract it and convert it. So if we have a look here at the process, we have this intake from the Mars atmosphere, and it's got a relatively high concentration of carbon dioxide. What it is that there'll be some filters. So what it'll do is it'll concentrate that carbon dioxide even more than it is naturally in the Martian atmosphere and compress it. And then what it does is it goes through an electrolysis process where we've got a solid oxide. Electrolysis, we usually use, or we know about electrolysis when we think about, let's say, if we were going to gold or silver plate something, then we would use electrolysis. Also, we use electrolysis when it comes to splitting water into hydrogen and oxygen, which is used very much in the food industry. But the thing is, this is actually using a solid oxide. And so what it is that some of that carbon dioxide will then be split into oxygen and carbon monoxide. And then what we do is we strip out the oxygen. That can often be done with filters and also with osmosis processes. We strip out the oxygen. The oxygen then gets analyzed in the MaxIQ unit to see how pure is that oxygen that we are getting out. Is it actually pure enough for humans to then breathe in? Because we certainly don't want carbon monoxide with that oxygen, because that is unbelievably poisonous to us. We also don't want any carbon dioxide remaining. So, and then what happens is that once we've measured how effective it is, then it all gets exhausted back into the atmosphere, the oxygen included. And the reason why it's all getting exhausted in this particular experiment is because the rover itself doesn't need to use the oxygen. When we've built the Martian habitat, of course, that oxygen will then go into the habitat, and then this exhaust gas will only be the remaining carbon dioxide and the carbon monoxide that's been created. So how has it been working? Apparently, it's really been working very well. We've got some stats over here. These statistics were after the first 2 months of operation. The report came out that said it had produced 122 grams or 4.3 ounces of Martian oxygen, twice as much as the scientists had predicted. So this is a real win, this MaxIQ process. So now we know we're really going to be able to use it when we go to Mars, or at least when we have human beings going to Mars. So let's get back to our agenda. And what I'd like to do now at this point is open it up to everybody. Let's have a discussion around these different topics. And also, if you have any questions in terms of, what are we going to look at in terms of solutions for this challenge?
I have a question sort of to get the conversation going a bit. That I think I asked last week in the webinar series as well. I'm really interested in how the work that's done to develop products for space and to solve problems in space, what implications that has for those of us who spend all of our time on Earth, and how some of these solutions might be applied either today or in the future. And so I'm wondering, for what you've shared so far, Judy, are there any sort of connection points with products that exist today, or that you could see us, adapting for problems that we face currently?
Rebecca, that's a really good point. If we take, for example, the water recycling, in a lot of situations, and I'm sure that all of us have noticed it, is that when we have with our climate, when we have these very bad weather conditions, and there's been really terrible floods recently in Libya, for example, sometimes on the coast of the US, when these storms come in and disrupt operations and destroy infrastructure. Often what happens is that the fresh water system, the potable water system, gets disrupted or gets damaged. And then we have this situation where we've got a lot of contaminated water all around and not a drop to drink. So the thing is that these systems can be containerized and then actually moved in when the rescue efforts arrive. These units are moved in, and so that what can happen is that contaminated, that dirty water can then actually be purified, so that at least one has drinking water, and then one can move on from there. So these processes have been used in a number of situations where, in terms of disaster recovery, so that is very, very applicable. Another thing is that with the International Space Station, resources are very, very scarce. So all of their power, all of their electricity needs to be generated using solar panels. And so, as you can imagine, they're keeping warm, they're doing all of their activities, plus they're running their water and air recycling system on solar panels, which means that we could definitely do this on Earth. So what it means is we could actually have installations in small villages and small towns, rural areas, where we could have purified water using this process, running on solar panels, renewable energy, clean energy. So this is definitely an example of where we learn from space and how we can apply it back on planet. Because it's only really when we're challenged by having too few resources. What do they say? Adversity is the mother of invention. So we really do innovate when we're in a situation where we have very limited resources. Regarding the MaxIQ process, it's really interesting, because the thing is that if you take, for example, if you have, certainly in the food industry, where one has controlled fermentation processes, what you have is that fermentation. The reasons why we have bubbles in, let's say, if, for example, if we have a beer or an ale or something like that, when it ferments, those bubbles actually come from carbon dioxide that are actually in solution. And then they're coming out of solution in the form of the bubbles. So what we have is we have a number of processes, especially in the food industry, which actually produce very high quality carbon dioxide. And what we could do is we could take those carbon dioxide streams, and we could utilize the MaxIQ process to then produce oxygen, which is very useful in a lot of other industrial processes. Or otherwise, what it could be is maybe it could actually be pressurized and it could be used in the medical industry, etc. We would just have to make absolutely sure that we had a very high quality carbon dioxide scrubbing process for that. In terms of the fossil fuel industry, when crude oil is processed and refined into petroleum and other products, there's two main off gases. The one is almost pure hydrogen, and the other one is almost pure carbon dioxide. And so the hydrogen is reused in the process. The hydrogen is very easy to get out of that stream. But the challenge with a lot of refineries is that they're actually venting this almost pure carbon dioxide. So if we could take that carbon dioxide and then put it through a MaxIQ process, we would then be able to recover some of the oxygen, which would be very, very useful in other processes. So yeah, you know, where do we have uses for oxygen apart from the medical processes? I'm not sure if you've noticed, but especially in areas where the weather has been unusually warm during the summer months, what happens is that the oxygen in the water for the aquatic life and the fish actually starts to strip out. Because the warmer the water, the less oxygen it can actually hold in solution. So what we find is that in areas where the coastlines are warming, where the oceans are warming, we're starting to lose a lot of aquatic life because they're actually running out of oxygen. They're suffocating. The warmer water cannot handle the larger biomass that's required. So the thing is, what we could be doing is we could be actually putting that oxygen into the water to help support aquatic life when we've got periods of unusual heat from a weather perspective. So yeah, there are a number of applications where we can take it and we can say, wow, we've learned this on Mars. How can we actually now try it again back on Earth? So that was a very long answer.
That was so helpful. Thank you.
Great. Do we have any other questions that relate to processes? Or I have got another slide for you. So let's have a look at this in terms of how do we take what we've been discussing and how do we actually now apply that in terms of this challenge that we're looking at when it comes to developing products, developing services for the space industry from an enterprising perspective. So the first thing we really need to look at is it's great to have an application, but can that application of the tech, do we have an application of the technology that's really practical? And also, how is it going to scale up to full production? So, and that is going to be the next challenge. Let's say, for example, with MaxIQ, that is an experiment that's been conducted by a little rover with a tiny little unit on Mars. So the thing is that how are we going to scale that so that it can actually support habitats, and how can it actually support like multiple human beings actually living on Mars for extended periods of time? So the scaling up is where the challenge is going to come in. From the perspective of the water recycling, the International Space Station is a fully functional unit. So that is at scale already. So we don't necessarily need to worry about that. But I'm sure that it took a pretty long time in the lab to get it to that point where they felt it could be scaled to the point where it actually could be safe and it could actually operate continuously and reliably on the International Space Station. So this is one of the things you really need to look at, is how we're going to scale it. It's one thing to be able to do a prototype, but the thing is it able to get to scale? The next thing is that in space, everything is scarce, as I mentioned before, and you'll find that the business models are different from here on Earth. So there are a number of products and services that are only going to be viable when they're used in space because of the scarcity. So the thing is that, for example, last week we discussed growing food in space, space agriculture, all of that kind of thing. So the thing is that what we may find is, let's say, for example, with resupply missions to the International Space Station, the Dragon module will take, the resupply missions will take, a number of prepared foods, meals, let's put it that way. If we were to calculate the cost of those meals, they are probably thousands of dollars each per meal, which we would never pay for some dehydrated whatever, something. Doesn't sound nice, but we would never pay thousands of dollars for that in a restaurant on Earth. However, because resources are so scarce in space, basically we need to pay that. So what you're going to find is that the pricing is very different. The volumes are going to be very different. So the business models will be different. So don't worry about, wow, it's not going to be viable on planet. What you need to consider is it going to be viable off planet? And the final consideration really to take into account is, can it be done without human intervention? So the MoXie experiment is a really good example where there's been no human intervention post-launch of the rover. And really it's perseverance that is managing that whole process, including collecting the data on the purity of the oxygen and retransmitting that back to Earth. So you really need to consider, can what we want to do be done without human intervention? Because for a very long time, we're going to be sending probes and rovers and robots to Mars before we actually send any human beings. So the habitats are going to have to be built by robots and 3D printers, and everything that is done there is going to have to be done by the robots before we arrive. So I just wanted to take those aspects and say, okay, so how do we take what we've learned and then apply that in terms of the challenge? Do we have any questions, Carrie, Rudo, anything from you, or are we going to conclude for today?
There's a lot of good information. We actually have a group that does, I don't know if you remember Ian from our workshop. Yeah, he leads one of our programs where students actually design a crewed mission to Mars. So this is very good information. Because one of the things they have, everything you talked about is some of the things they have to consider. So that's great. Great.
Excellent. Great.
Judy, I have just one final question, sort of reflecting on all that you've shared so far today, which has been so fascinating and helpful. I imagine that a lot of teams might be thinking like, well, if we've solved all of these problems, what else is there to do? But I know that there are still countless things as it relates to environmental systems in space that we actually don't have great solutions for, we could improve on. So I wonder if, there are just a couple that come to mind right away. If you could sort of wave a magic wand and they could be solved, what would those problems be?
We definitely haven't solved everything when it comes to growing food. We definitely haven't solved the challenges when it comes to irrigating large volumes of plants for it to actually be sustainable. from that perspective. Another thing that we really probably still challenged by is dealing with the solar radiation on our way to Mars and also on the surface of Mars. So we're very, very lucky on planet Earth, but I guess we've adapted to it. That's why we can live here, is that because of our magnetic field. So our magnetic field that protects our planet, what it does is it protects us from a lot of solar radiation and the solar winds. Whereas that is not the same situation when we are above the Van Allen belts. And when we're on our way to Mars, we're really going to need to have a look at how we're going to protect ourselves, and then also on the surface of Mars. So you may have seen in a number of movies or a number of documentaries about being on Mars, one of the things is we may have to live underground. That's because we're really, really concerned about how we're going to deal with this radiation. So yeah, moving around on planet is going to be difficult, because we have to find a very sustainable way of protecting ourselves from radiation. One of the prevailing theories at the moment is that we can use water in the shell of our spaceship to protect us from the solar radiation on our way to Mars. But wow, that is such a heavy solution. That is really, really, that's going to be difficult. So I listened to a podcast by Neil deGrasse Tyson some months back, where he was talking about the rocket and the fuel equation. And basically what it is that for every pound that we need to get beyond Earth's gravity, it's going to take 100 pounds of fuel. So getting the water, if we have water in the shell of our spaceship, it's going to be unbelievably heavy. So one of the solutions could be mining water, mining ice on the moon on the way there. We're going to have the same challenge on the lunar surface as well, because that's beyond the magnetic field. So a lot of these challenges we're going to solve on the moon before we go to Mars. And so maybe that's also a way of thinking about it in terms of this challenge, is how do we get something to work on the lunar surface, and then we scale it to perhaps work on Mars, because Mars is going to be further away. It's got more gravity, etc. A lot of applications, we actually do need gravity. Even for our own digestive systems, we need gravity. So the thing is that a lot of things are actually going to work more easily on the moon than they are in orbit or on the way there in weightlessness.
That's so helpful. Thanks, Judy.
Great. Okay, I think with that, I'm not seeing anything in the chat either. With that, I'd like to conclude and say thank you to all of you for joining us today. And also greetings to those who weren't able to join us and who are watching us on the recording. And we'll make sure that everybody gets a copy of the recording with Judy's ums and ahs all edited out.